Okay, so we'll start. And, so today is the last lecture on jets and synchronous black holes. Before I start off, do you have any good questions on what we did yesterday? No? And you can ask me in between as well. So what today we will do is that we will look at a few different aspects. They appear somewhat disjointed, but in a way they are all connected. And some of it, a bit of it actually we also covered. So a little bit of it will be revision, but otherwise it will be entirely. So the questions which we are planning to do. We will give a call to Santosh. Something that's locked in each other. I don't know what arm means, something. One more thing, see that. Okay, fine. Aniket, there's no problem. Okay. So the questions we'll ask ourselves are, so how fast are the jets moving? And we'll also look at its consistency with the unified scheme which you talked about. The way galaxies appear different because of their orientation, but intrinsically similar objects, is what is close by the problem by unification schemes for IUCAA. We have a better correlation and launching of jets. We will highlight to you the kind of recent results that one is obtaining and what clues they may be giving us. Then exploring these jet connections, triggering and launching of powerful jets and the current or episode intelligence. It's a big list over there, but we try to finish it. Okay, also you can start it. Okay, now how fast are the jets move? From various lectures, what will you see? What will your answer be?
Close to the speed.
Close to the speed of light. And why do you say that?
Because the amount of time that they have left traveled from the host galaxy or the black hole that they through them and the distance they are at, you can calculate. And it comes from the near to the speed.
This comment comes from near to. Is that, do you all agree with that answer? See, there are two things. There are two things which you should not mix up. One is that the Lorentz factor of the electrons. Okay, that can be 10 to the power 4, 5, 6, whatever, thousands or billions. If you're talking about exclusive numbers. The other is the Lorentz factor of the bulk motion of each other. For example, I may have a blob of plasma in which electrons are zipping around at thousands and thousands of Lorentz factor. But that blob may be stationary. So when one is talking about a jet, one is not talking about the motion of electrons, but one is talking about the bulk motion of the plasma which is emitting the radiation. Okay. Now it is not that now how would you measure speed? As you said, you go and look at the position at one point of time, look at the position at another point of time, you know the distance it has traveled, and you divide it by the time because you keep track of how much time is elapsed. Distance divided by time is the velocity. Simple explanation, right? Now, let's look at this, how fast is just moving. So this is the jet of M87 on various scales. But if I want to measure motion, then I need a reference point, right? I need a compact component that I need to measure the motion of that component relative to that stationary component. Now the nucleus is taken to be stationary, and there have been one or two experiments to show that it is indeed stationary. Then I need a compact component. And finding this compact component is possible in the case of the nuclear jets. Okay? Because right in the nucleus, when the jets are squirting out from the nucleus, that's the time when they're very compact. And later they expand. Now, if it expands out, the problem is that the blob is large and the motion is very small. It may be milliarc second, maybe a blob is 1 arc second. It will be very difficult to detect motion. So the motion, the determination of motion or velocities you can do in the case of the nuclear jets, right? Now, this is just shows the metric state, but you need a compact feature. For example, in this jet in M87 over here, it's on Vernier scales. I mean, there are features that's not very clear. What I want to mention is that you need a distinct feature. If there isn't a distinct feature, then it is difficult to determine the motion. The other thing I wanted to mention is that we can do that for the nuclear or small scale jets. But in the large scale jets, because components are larger, and if you look at it in the kind of real resolutions we'll talk about, you will not see any structure at all. You'll resolve it out. Just as in the previous image, when you look at high resolution, when you look at it at high resolution, you can see that in this component over here, jet, all that you're seeing is this little bit of it. That's what's programmed. So once you go to higher resolutions, your antennas are further apart and the larger scale structure you miss out. So when you want to measure motion of a few milliseconds or even less than that, you need the high resolution because you need resolution to monitor the motion. And you can only pick up the most compact features. Right? The other thing I want you to know, note over here, is that this is a giant radio galaxy. A giant radio galaxy is defined to be greater than about 700 kiloparsec. It's just a definition. Earlier it used to be 1 megaparsec. And you remember what a parsec is? What's a parsec?
3.2 light years.
3.26 light years. Very good. 3.26 light years. So, with a change in the cosmological parameters, people have set it at 700 kiloparsecs. Now, if you look at this, this is the large scale jet, which is over here, and this is the nuclear jet, which at the nuclear jet here. But what you see in this giant radio galaxy is that the nuclear jet and the large scale jet are nearly along the same axis, and also the sidedness is the same. Right? So I want you to remember that. And that will be generally true in all cases. In some subset of sources, the nuclear and the large scale jet appear misaligned, but we will come to that in time permits. But generally, the ejection axis of the largest small scale jet are same. If there is precession, it will change. But for most cases, it will be the same.
Nuclear jet is the part of the jet that is closer to the black hole?
Closer to the black hole. Closer to the black hole. Yeah. So the higher the resolution you get, the closer and closer you go to the black hole. We'll talk about the kind of resolutions that one is being able to obtain these days. That will see a jump. But just remember that they're asymmetric in the same sense. The sense that the large scale jet is pointing towards a knot, the nuclear jet also points towards a knot. Okay, and they're roughly aligned in most cases. This is the jet in 3273. The famous quasar that we talked about, the first quasar to get identified. This is a large scale structure, and this nuclear jet has been made with a dropped in England called the Manchester Radio Interferometer, and this is a very large baseline array, very long baseline array. And this is at near scale resolution, milliarc second. All of this over here is right in the code. And here I can see these two plots, these two peaks of emission. So I can keep observing the source year after year after year after year, look at the motion, and then find out how far it is. And if I do that, then what I find is that there are two examples over here. Then I get a velocity which is more than that of light. Okay, so if you just for many of these objects, if you just measure the motion and divide it by the velocity, divided by the time, you get a velocity which is greater than that of light. And this phenomenon is referred to as circular motion because of its apparent motion. And as Verdi will explain to you, it doesn't vary special. And the explanation is very simple. If one of you want to explain, I will not do it. One of you want to explain why it happens?
Because as we see it at a later point of time, it would have moved much closer to us.
Sorry. That's part of the answer. But if it is just projection, that will not give you a velocity greater than a blank. Because what you see in projection will always be smaller in the true length. Right? So you have actually divided a small distance by time. So you get less velocity just in that. That was the only part of the explanation. Because ultimately you're dividing distance by time to get a velocity. And if you project it, you get a shorter distance. It's like the jet is coming towards you and you project it. This is the distance. Okay. So let me try and just quickly go through it because this is quite interesting and it is very basic sort of arguments. But people actually initially when this was discovered, radio astronomy was still in its infancy. And the bulk of the astronomers are optical astronomers and they sort of didn't believe the results and got some problem with the experiment. Today we know that that is not the case. That a lot of objects that appear to exhibit. Now, also, I want you to notice that all these sources, the nuclear components are quite strong, right? You saw images of signal string, for example, where the core was very puny compared to the overall flux density of the source, but the cores are strong. And because it is strong, one could put these experiments in the early days of very strong experiment. Is it confined to only the radio? Generally, it's in the radio, but this is one case where superluminal motion has also been detected in optical regions. This is the HST image of jet in M87. It's this little part which they monitor these two blobs going out and they get velocities of expected velocity. Now, you can work this out yourself, but I'll just try to explain to you what's happening. What you said about seeing in projection is correct, but that is not the entire story because what you see over here, if I take a blob which started from here and is reached over here, then this is the distance it has traveled, and let's say phi is the angular inclination to the diagonal side, then this is the distance that it will appear to have traveled. Okay? But I have to divide it by time, right? And that is where the crux of the explanation is. Now, if you think about a wavefront which is emitted when this blob was over here, and a wavefront which is emitted when it was over here, then it is a time difference between those two pulses that you register as the time that this blob has traveled from this point, from the origin to this point. What is that time? It will be the difference between the two wavefronts, and this is CT, this is VT cosine phi, that is the distance, and you divide it by the velocity of light, you get a time. So physically what is happening is that if you think of one wavefront coming at a point when it was in the origin, and this component is moving almost keeping up with the wavefront. Not quite, but almost keeping up. So what is happening is that when you measure the time difference, the time is really getting squashed. Right? If it was exactly at the velocity of light, you wouldn't see a time difference between the two wavefronts. The time is getting squashed because the object is almost keeping up with the wavefront. Right? And you can express it in this way because it is just this VT sine phi divided by VT upon C, which will be divided by C, divided by C over here. So TTs will cancel out over there, and you can easily derive this expression of the apparent velocity is equal to beta, the velocity V upon C, which is traveling, divided by 1 minus beta cosine. So if you can see over here that if you take a small angle, phi equal to 5 degrees, velocity nearly that of light, you can get apparent velocities which are greater than light. Now, to understand superluminal motion, you can only see it if the velocity of the component is very close to the velocity of light. So we know from that these jets are squirting out from the nucleus at a velocity close to that of light. If V was very small, if you look at this expression, for example, if beta is not 0.99 c, but 0.0001 c, then you will not be superluminal motion. You can plug in the numbers over here, and you're not going to be able to see. So you need the components in the jet to be moving at a most velocity of light. Now, what happens if the jet is coming directly towards you? I put a small angle of 5 degrees. Do you see superluminal motion? If it is coming directly at you?
You wouldn't see motion.
No. And if you put phi equal to 0, sine 0 is 0, so you, okay. And if you think about it physically, if you have a jet coming towards you, exactly, an idealized situation, you're not going to see any displacement. You don't see any displacement towards what distance is it traveling. Okay. But the other interesting thing which happens when you when a jet of plasma is coming directly at you is that relativistic effects enhance the flux density of the lava plasma. Okay. And that's the expression which I have written here, that the observed flux density can increase by a large factor. And you can derive this in different ways. One can do it by looking at the special relativistic transformations, or when you do electrodynamics, you find that the intensity divided by the cube of the frequency is a Lorentz quantity, and you could use the Doppler frequency for frequency and work outputs. But basically, you can see this gamma into 1 minus theta cosine phi to the power of a plus alpha. That is 2 and 3 is like a model dependent. You see the short y. And here, even if phi is equal to 0, you get a huge boost in the flux density. Beta is very high. So you can see this 0.999, 1 minus 0.999, 0.00 something, you raise it to some power, multiplied by gamma. It's a small number, and then you divide this by that, you get it. So all you need to remember is that when plasmons or a jet is coming towards you, its flux density will also get enhanced. Okay? And you see those strong cores in the sources which I pointed out, because the flux density is getting enhanced. Right? Now, let's go one step further. Okay? What happens if it's going away from you? You're not going to see superluminal motion. Okay? That's because your wavefront is coming this way, your block is going that way. Right? But your flux density of the component which is going away from you will be diminished. Right? So when a blob of plasma is coming towards you, flux density goes up. When it is going down, when it is going away, it actually decreases. And even when it is transversed to the line of sight, if you put cos 90 over here, cos 90 is 0, you'll find S intrinsic divided by pulse non-emphatic, the power of 8%. So even if it is on the sky plane, the flux density will actually decrease. Right? In the sky plane or beyond that, it's going to decrease, and if it is coming towards you, it's going to increase. Okay? Just remember that, because we are going to apply that. So when you look at the ratio of the approaching to the receding component, I will get this. It's just a ratio of these two numbers. RS is the ratio of the approaching component to the receding component. Right? It should be 1 plus beta cosine phi or 1 minus beta cosine phi. What happens now? You put phi equal to 1. Play around with these numbers, plugging in values. I've just put in 1 for your reference that V is merely the velocity of light and phi is the flux density ratio is about 3 to 10 to the power of 4, which is 30,000. You can see it's a large ratio, right? Now, where does this get applied? Because all the jets that we've seen for which superluminal motion is measured right now are all one-sided jets. Right? So it is not that the other one doesn't exist, but the other one is going exactly the opposite direction. So if it's going in the opposite direction, this flux density is going to decrease because of the Doppler effects. If it decreases, it will be below your detection, or it could be below detection. So we try to understand the asymmetry of the jets in terms of the relativistic beaming effects, where the jet which you're seeing is the one which is approaching you, and the one which you do not see is the one which is receding away. Right? So you know that is now in the small scale jets, we could measure the motion. And we cannot measure spectral lines over here because it's all continuous motion. There's no line over there where we can measure the shift. Right? Otherwise, we could have been able to measure the shift and say what velocity is. The large scale jets, as we mentioned, is these compact components, ultra compact components that you need to measure and keep measuring the displacement. It's not there. So how do we actually infer that with one velocity is more. Remember when I showed you the image of the giant galaxy of GC6251, I told you that the small and the large cube jets are pointing in the same direction. If they're pointing in the same direction, explanation for one is consistent with high velocities and relativistic effects, then you would naturally sort of think that that is also what is responsible for the large cube jets. Right? Because it's pointing in the same direction, it is asymmetric in the same direction. So it is natural to assume that. But can we do a little better than that? Can we do a little better than that? To at least establish that the large scale jet is on the approaching side. If you can establish that, then you can be more certain that that is perhaps the right explanation. How do we do that? How do we do that? That goes back to a very simple sort of test which was done not very long time ago. This is a quasar event just showing the remind you of the image that it's a highly asymmetric jet over here, and this object is a quasar. This is the nuclear or co-component. These are the extended lobes of the. If you look at the expression per year, as I mentioned, if the velocity is low, for example, if it is 0.1 or 0.2 or 0.01, the source would be raised to this ratio would be not large. But if the velocities are large, the angles are small, then the ratio is large. If the velocities are small, the ratio is small. If the angles of inclination are large, then the ratio is again small. Okay? So the fact that in this particular source, I see the jet which is asymmetric, indicates that the velocity of the jet is large, whereas the endpoints where it is trying to push its way to the general interstellar medium, the velocities are small, so the outer lobes look symmetric. But the jet velocities are large, so the jet appears one-sided, although intrinsically it is two-sided. Now, for a few minutes, I'll just introduce the concept of trying to establish that it is indeed on the approach. How do we do that? That actually depends on a little sort of little concept of polarization. You know what polarized light is, right? What is polarized light?
Vibrating.
Sorry.
Light vibrating in one plane.
Okay, I mean, the electric vector has a preferred orientation, right? Otherwise, it will be all random. Okay. Now, as I mentioned yesterday, that these jets are polarized, and although there is a random component, and there is a net degree of polarization which you observe. All right. Now let's see what happens if you. And you're familiar with Faraday rotation? Yeah. You're familiar with Faraday rotation? When the electric vector rotates, it goes through a determinate medium. Yeah. Let me just illustrate that. Slide. Okay. Let me just to remind you all then that if there is a particular angle, right, along which the electric vector is inclined, right? Let's say whatever be the angle. Right? Now, if that radiation passes through a magnetoionic medium, the electric vector is going to rotate. Right? Okay, and by how much it rotates depends on the electron density, the parallel component of the magnetic field, and is proportional to the square of the wavelength. Right? Okay. I will derive this. There's no time to derive it, but the thing is that just take my word for it right now. That it will rotate. So the longer the wavelength, the more the rotation. That's the strongest. Now, and higher electron density has more rotation. Now let's see what happens if there is a jet or a source where the fields are connected. Okay. Interesting. Now it passes through a medium. Okay. The medium is never perfectly uniform. Right? It will have irregularities of different sizes, different densities, and again different magnetic fields. So if you were to sort of put a magnetoionic medium with each cell over here having a different electron density in a component, they will all get rotated by different amounts. Right? That is clear? Yeah? Because it's just proportional to any B parallel lambda square. So suppose I'm observing at a given lambda, whatever the lambda right now, if the electron density and V parallel are different for each cell, each vector will look at different amounts. Now I try to observe this telescope. Here, all the vectors are in the same direction, they will add up and give me a high value of polarization. Over here, it's obviously going to decrease, right? Because they're all in random directions. If it's completely random, you may get zero polarization. But it's definitely going to decrease. Now, what is happening is that if I had a jet over here, I have a nucleus over here, I have a nucleus which is a core, I have a jet coming out of here, I have a lobe over here, I have a lobe over here, and I'm observing over here. Alright? Now, this particular object has a galaxy associated, right? Has a galaxy or a quasar. A quasar is also a galaxy with an abnormally luminous nuclei. So I find that this object, this lobe, is going through this magnetoid. Because this lobe isn't, right? Yeah. So what will happen is that when I look at the polarization of this, it's going to get flipped about much more than what I would get for this sudden. So, and remember that it's proportional to the square of the wavelength. So if I were to make measurements at 2 wavelengths, I will make my measurements at say 5 gigahertz and say 1.4. Just 2 frequencies. This corresponds to a wavelength of 6 centimeters. This corresponds to a wavelength of 20 centimeters. So at a longer wavelength, they will be zipping around a lot, right? So at longer wavelength, I will get less polarization. For the northern one. The southern one affected a little bit, but not very much. So if I can show that components on the other side are all getting depolarized, then I know that the jet is approaching us. Is it clear? Yeah? Okay, sure. So, for example, what I say is that emission from here is going through the interstellar medium of the galaxy, which is the magnetoionic galaxy, the magnetic field as ionized plasma. Okay. Now, the amount by which the vectors rotate, rotation which I shown here, is proportional to square of the V. So if I zip around these a lot more, the net polarization is going to decrease. So net polarization is at the longer way. Now, if I look at these 2 lobes over here, one of them is going through the medium, the other one is not. So the one that's going through the medium will be affected much more by these Faraday effects, and therefore the polarization is going to decrease at the longer way. Is it clear? Yeah. What do we see? And if we can establish that, then we know that the one which is facing the jet is on the approaching side. Okay? So on the opposite side, I would expect it to polarize. That is what I see over here. So you can see this is at 6 centimeters, at 5 gigahertz, and these little vectors which you see, you know the degree of polarization at longer wavelengths is almost gone. And I can take the ratios of it as well, and you can see that there is hardly any depolarization as we call it. So polarization at 20 versus 6 is nearly 1. These are the errors over here. Okay, over here it has come down. So we know that this has been done for many objects. It was done by a graduate student at Jordan. In fact, we were there together, somehow together as well, and it's referred to as a line character effect. To show that the approaching jet, the one-sided jet, is approaching us. Alright. Now I will go back a little bit onto the final of writing class 1 and 2. Here, for example, in the class 2 objects, this is a quasar. I see a very narrow collimated jet, and we know now that this is approaching us. Now I can use that flux density ratio formula to put a limit on the velocity. I don't see the other jet, but I know it should be at least fainter than a certain band. Otherwise, I would have seen it. So from the observed flux density ratio, I can put an estimate of the velocity assuming a certain angle. Okay. So I can do that, and then I get velocities for the large scale jets to be order of 0.2, 0.3, 0.4. It's not 0.99 c, but it is still a fair fraction of the velocity of light. If I look at a Federer of Riley class 1 objects here, they are not asymmetric, they are reasonably symmetric. And we understand by saying that these jets actually slow down much more rapidly. They're not very well coordinated, they interact much more with interstellar medium. They're low Mach number jets, they're subsonic, they entrain material from the surroundings, and because their velocities are low, the expected flux density ratio is low. So once the velocity is low, your ratios will also be small. Alright? So FR1 jets, the Federer class 1 jets, they're different from the FR2 jets. The differences in magnetic field, etc., but they're not good metrics. You just look at velocity. Right? So here is the synthesis jet we saw earlier, and this one you can see there is a bit of a counter jet in here, which take care of the years. But you can see that it's a very small core. This is a galaxy. The quasars are more prominent cores, and these are the modes. So it's just quasars have much more prominent jets, and they're usually one-sided. And as I mentioned, as I mentioned earlier, I keep mentioning that FR1 jets are, they diffuse out, they decollimate quite rapidly. And these jets have been actually, again, we can't measure points of emission over there. But these two astronomers, Robert Lang and Eric Brighton, they have done some detailed modeling of the observations. So this is their putting all the hydrodynamics and orientations, emissivity, etc. And they try to reproduce these observations. And when you do that, also put in velocity, see that right in the nuclear region, this is FR1 jets, they're close to the velocity. But they decelerate quickly, right in the center region. So by modeling also one can try and get velocity, but the more direct measurements are actually monitor motion of the subjects. Now, what relevance does it have for a unified scheme? I should look at what relevance does it have for a unified scheme? Okay. Now let's see what because that will tie in the jets together. So do you want to sort of suggest your ideas of what we've discussed till now and what we've discussed yesterday in terms of the unified scheme of EGN? How can we connect them? I mean, just make your suggestions. It doesn't matter if it's right or wrong. Any suggestions?
Please. What? Repeat, please.
Sorry.
Repeat what?
No, what I'm saying is that we'll try and tie in what we have learned about jets today so far with the unified scheme which we talked about yesterday. Okay. Let's want to say, you want to add anything? Want to say something? No? Okay. Let's look at it. What did we say yesterday? That we said broad lines. Let's look at radio loud objects, which are the radio galaxies and quasars, right? And we also know that radio galaxies and quasars, look at it. Radio galaxies, quasars, and also the other. So radio galaxies, they get classified into FR1, right? FR1. Now let's look at this. So what did we say yesterday? And this is what Vaidhi also taught you all. That for a quasar, okay, I can see the blot lines, so it is at a small angle to the line side. Right? And what did we learn today? That if it is at a small angle to the line of sight, you will see highly asymmetric jets. Right? You will also see superluminous motion. If it is at a large angle, you will not see superluminous motion. Right? And you will see more symmetric jets. And what did we say? What did we say? What we learned was that when you look at a large angle, you see the galaxies because you don't see the broad angle. Right? Yeah. At a large angle, you'll also see more symmetric jets, and you'll also not see superluminal motion. So by and large, what I expect is that I would see in quasars, I'm going to see superluminal motion, and I'm also going to see jet asymmetry to more pronounced. And if you look at those jets, for example, the quasar which I showed you, and galaxy, say just two examples, then you'll see that this is 3C273, which is a quasar. This is 3C. This is Cygnus A, which is a galaxy. You see the field in this proper kind of jet over here. And the jet is also quite big because it is at a large angle. This is illustrated in FR1 and FR2 as well, which is a quasar over here. This is a FR1 galaxy. So because galaxies in this model are at large angles, you will see that they are, you will not see superluminal motion. Generally, there may be some exceptions, some galaxies may be at a small angle, but the broad properties get weaker, and when you see them, they are more symmetric. So the properties of jet are consistent with this overall picture. Those galaxies are the ones where you don't see prominent emission bands. So they're at large angles to the line of sight. If they're at large angles to the line of sight, you will see jets which are more symmetric and not going to see superlumination. Okay. And that is what is consistent with the observations. Now, orientation, you cannot turn an FR1 object into an FR2 object. Something which has hotspots, I can't turn it around and make the hotspots. So in these unified schemes, what has happened is that to make the log all the parameters consistent, I would say small angle, small. These two, the F1 objects and the real-life objects are the pairs. Okay? This is angle of inclination is small, and the galaxy or one galaxy, the phi is large. In terms of FR2, when phi is larger than the and where phi is small are the quasars. Okay. Is that clear? Not clear. Is it clear? No. Last sentence is that, see, when I want to, if I take a class of objects, and I'm trying to say that some of the objects are inclined at small angles towards us, and some are at large angles towards us, right? So it's a population of objects, they'll be randomly distributed in the sky, but they appear to be different because some of these objects are at small angles and some are at large angles. What we are saying is that the quasars and the real-life type of objects, which are very strong cores, their flux densities enhanced, their prominent jets displayed, they have superluminal motion, are at small angles, right? So then you need an unbeamed counterpart for that, right? At large angles. So the real-like objects, the unbeamed or the large angle counterparts are the FR1 radio galaxies. Whereas for the quasars, which have hotspots, are the FR2 radio galaxies, which also have hotspots. So we want to make the large field structure also consistent. Is it clear? Okay. Sorry. Okay.
Kind of
Let me try. From the basic picture, you're happy that quasars are inclined at small angles, right? From the basic picture, you're happy that galaxies are inclined at large angles, right? Now, the fact that quasars have more asymmetric jets, because you expect more asymmetry because of relativistic heating effects in sources which are at small angles, right? So that property is consistent with quasars. That's what happens. So by the same token, you should get more symmetric jets and galaxies because they're at large angles. And that is what you see. Now quasars are at small angles. For superluminal motion, you require small angles to back to side. So you should see much more superluminal motion in quasars and BL-like objects, which are also inclined at small angles, compared to the galaxies. That is what you see. So quasars and BL-like objects are at small angles, and galaxies, both FR1 and FR2, are at large angles. But I can't turn a quasar, which has hotspots at the other end, into an FR2 into an FR1 radio galaxy without hotspots, but just changing the angle. So, to match up the large scale properties, what we need to do is that we need to match up the BL-like scale large scale structure, which are also generally diffuse, with the FR1 objects. So there are two categories of objects over here which are at small angles. One is the quasars, the other is the BL-like objects. The unbeamed counterparts, or the large angle counterparts of these, are for the BL-like objects, the FR1 galaxies, and for the quasars, the FR2 galaxies. Is that clear?
Yeah.
Yeah. Is it clear? Yeah. Okay. I think we're running out of time, so I will not get into this further, but basically it's the same idea which we talked about here. Now, here I will just sort of go through a little rapidly because it's just showing you pictures. Now, we want to try and understand the basic coordination of the jets. All right? We know that they start off. We also want to understand actually where did the jets originate. We saw that we can explain the energy output by equation of the supermassive black hole with an equation. But where does the jet exactly originate? Is it 100 times Schwarzschild rate? Is it 50 times? Is it 1,000 times? And how does it originate? Does it originate in this picture or in the magnetosphere? Put it down. So these are aspects which we have been able to only make a dent in recent years. And the reason is that you really need the resolution to be able to probe very close to the black hole. And we'll see briefly what's the kind of resolution. Okay? Now, these are very early attempts which some of us did and some of our collaborators and colleagues did. Also, just look at the jet width or the hotspot size as a function of size of the source. And then we find that it has a linear relationship as though it has a conical kind of structure, and the angle which the hotspot subtends is roughly the same, but the size keeps increasing as the source expands. So these were some very early, which really relied on this measurement sizing, improved but early. But what has happened more recently is that one has been able to observe these jets with higher and higher resolutions and closer to the black hole. So we are able to measure the sizes of jets at sub-parsec scales. And then, and this is a field which is actually developed because we only have measurements for about a dozen sources right now. And we are trying to understand the shapes of these sources. For example, if it's a parabolic jet like this, then you have the jet of the width of the jet, which will vary with distance from the core as 0.5. If it's a conical jet, it will actually go directly as distance from the core. And if it was a completely cylindrical, then the weight will not depend on distance, right? It's a cylinder. So we've been able to make this measurement and try and find out what is going on. And we find a wide variety of things. In many sources, it seems to make a transition from a parabolic kind of slope of 0.5, which is 0.45, which is close to 0.5. This is a giant radio galaxy, which is 315. And if you go further down, then it becomes more like a conical. It's not exactly conical, but approaching that. And we've been able to do this for more and more objects. This is the same Relativistic jet, but when you observe it in high resolutions, we also find we also can determine field orientations, and from field orientations, we can also infer that there is a toroidal field over here. And these are all exciting ideas which are beginning to unfold right now. So as the jet expands, one is of course measuring how the wind changes with distance. The other question to ask oneself is, what is causing the change? Is it magnetic fields which are moving around, giving rise to V-cross-B forces which are keeping them in track along an axis? Or is it the external pressure which is actually make the jets combine? Or is it just a free-flowing jet and material is just shooting out at a certain velocity? So we need observations to constrain all that. And these are slowly happening. The fact that here, without getting into details, where is a field which is going away from you, this is the orientation of the magnetic field. So one will begin to get evidences on sub-parsec scales, fraction of a parsec, with millisecond resolutions about the orientation of the square. So these are being modeled right now in terms of both a combination of magnetic fields as well as external densities playing a role in collimation objects. This is another one, Centaurus A, one of the nearby galaxies, and this has been imaged with the Horizon Telescope. To say a little bit more about it, I put this in just to illustrate a wide variety that one is looking to get. Here it is about 0.33, the width varying in distance, whereas M87 it was more conical, 384 it is more sort of cylindrical close to it, and these are things in between. So we're beginning to get more and more information, but it is right rather than right now. I will close this little bit by actually showing you this particular image, which has appeared in the April issue of Nature, just a month and a half ago. This is the M87 nuclear region where the black hole was imaged a couple of years ago and made headlines across the world. This is very right within the nucleus. This is the large scale jet. And what you see over here in this image, this was made with a resolution of a few tenths of micro-arc seconds. And you can only see the material in the disk around the black. The central part is the black. With slightly, and you didn't see the jets at all, back on the image was published. With slightly coarser resolution, they have become as jets. And they believe that these extensions that you see are signs of the accretion disk around the black hole, from which the jet is being launched. So what you see over here is a jet is being launched close to the accretion disk. Now, whether this is true of all sources, we have no idea. But at least this is a plausible scenario where a jet is being launched in the black hole. People used to model it in terms of magnetic fields spreading the black hole, going, these build up magnetic stresses with G2. But now we know from this is one source that it is originating in the disk of the black hole itself. And what you can see over here is the opening angle is very large, right? Compared to the very small opening angle of the large jet. So it opens up, then it gets collimated. So we are beginning to get the first glimpses of how jets are actually launched in active electric nuclei. To do that, you have had to make observations of very high angular resolution. How high? At a level of micro-arcs, 10, 20, 30 micro-arcs. To get a kind of feeling which that means, I sort of put this slide to show that if you take a 5 rupee coin and hold it at a distance of 100 meters, 100 meters is familiar with a 100-meter race, right? It will subtend about 47 arcs. That is slightly poorer than the resolution of the human eye. That's slightly sort of finer, smaller. Human eye is roughly about an arc minute. It depends on the day or night because it keeps going as well. But of that order. If you put it at 1,000 kilometers, we get into the milli-arc second. Right? So if you put it at 1,000 kilometers as a crow flies from Pune to Delhi or something like that, so if you put it up, it will get a milli-arc second. But today we are imaging these objects right near the black hole at micro-arc second. What does it mean? That means if I put this coin at a distance of about 10 to the power of 5 kilometers, which is 100,000 kilometers, that is the angle that it is at. And that is the resolution that it's trying to do. And that is quite amazing. That's an amazing technological achievement. I mean, 100,000 kilometers is 1/3, roughly 1/3. Distance to the moon is about 480,000 kilometers, right? Something like that. So it is nearly 1/3 of the distance to the moon. You hold a 5 rupee coin, and the resolution, the angle which it subtends, that's the kind of resolution you're getting with modern interferometry. So, for example, to translate into something on the moon, it's not even, a watermelon or a pineapple on the moon. Even if you take a normal sized orange, or a Musumbia or put it in the moon, this is the kind of angle. So that's the kind of resolution which you get. How do you get that? By getting to smaller and smaller. Rayleigh's criterion, you all remember? Lambda upon T. Okay, lambda you make it smaller and smaller. But the challenge is actually making interferometry in small wavelengths for large distances, and you make T as large as possible. So the two telescopes, the Event Horizon Telescope, which operates at millimeter wavelengths, that image of the black hole was made at a wavelength of 1.3 millimeters, and you can see the telescope right from the South Pole to Europe to Hawaii, they spread all over. There is also a Greenland telescope right now, and this was made with what's called a global millimeter wave. Slightly different set of telescopes, but that earlier, the next image which I showed you with the launching of the jets, that was made with the global millimeter VLBI array. But basically, telescopes spread across the world, spread across the earth, operating at millimeters. Okay, and that's the kind of resolution. So we're getting the first glimpses that these jets are being launched from the accretion disk itself with the kind of resolutions that we are able to achieve. But before we were able to achieve these resolutions, we still had an inkling that the accretion disk had an important role to play in the launching of the jets. And that was by looking at properties which link the jet to the disk. Now, for example, I can't usually resolve the disk, right? And now we're beginning to see a little bit of these resolutions. But the disk is where all these high energy photons originate. And the high energy photons will go and ionize the gas clouds and we'll see emission lines from it. So if I can link the emission line properties to the jet power, then I know that there's some fundamental link even if I can't figure out all the physics of it. So some of the early suggestions that disks and jets are actually coupled in some way came from looking at correlations of line luminosity versus the jet power. Jet power is essentially related to jet luminosity. So you can see that this is the jet power at the narrow line luminosity and the oxygen 3 line. Typically ionized oxygen here. 3 line that I shared, and you can see a very nice correlation. So these gave us a first hint that this and jet are correlated, and there is an intimate relationship. Now, we mentioned about a small fraction of radio of galaxies being extremely luminous in the radio. What percentage did we say? Roughly about 10%. Roughly about 10% are luminous radio. But when we look at galaxies with bulges, they all have a supermassive black hole. So now the question to ask oneself is that if all these galaxies with bulges have supermassive black holes in there, what is it that makes some of them become radio loud, luminous in the radio, shooting out these powerful jets, whereas others seem to be radio quiet or radio weak? What are the fundamental parameters that govern them? And how does one address that? So this particular relationship, actually, what it shows you, did somebody show you this fidelity? No. What is plotted over here is an estimate of the mass of the black hole. For all kinds of galaxies, right from the Milky Way to nearby galaxies to M87 we keep talking about, and the velocity dispersion in the bulge of the galaxy. Spiral galaxies have a bulge, right? And then the disk, whereas elliptical galaxies are all bulged into spiral arms. So if you look at the velocity dispersion of stars in this bulge, they are intimately related to the mass of the black hole. And all galaxies which have a bulge have a supermassive black hole. Now, the question we try to ask ourselves is two things. We know that the disk and the radio are connected, are related heat sources which are luminous radio sources with powerful jets But we also see that that's only a small fraction, okay, of the total population of other galaxies. So what triggers the formation of these sources? And that's the question which we try to understand. Now, the fact that these are related, in addition to the correlation I just mentioned, we will look at other aspects as well. In some cases, we can also measure the spin of the black hole, and are these related in any way? And we will try to explore not just the correlation between the optical luminosity, aligned luminosity, and the radial power, but then also try to look at correlations between multidimensional analysis of X-ray luminosity, which is for the disk, mass of the black hole, and the radial luminosity. And there seems to be a very good correlation which is referred to as a fundamental plane of black hole galaxies, right from stellar mass black holes, microquasars, to galaxies and quasars. So basic physics may be similar, and this sort of hints towards that the disk and the Rajki radial properties are related, but we still have no much of a clue as to why only 10% of either galaxies or quasars are luminous in radial. Okay. We have 15 or 20 minutes, so we will finish. But do you have any questions at this point? Before we try to understand why a certain fraction may be radial.
How do we know that the galaxies with a bulge have a supermassive black hole?
Sorry?
How do we know that all galaxies with a bulge have a supermassive black hole?
Okay, that relates to trying to find out if there's a black hole and estimate its mass. I've already touched upon that, but not very much, at least from the slides. But if there is a massive object, for example, in our galaxy, we have estimated the presence of a supermassive black hole with the motions of good stars around it, right? In other galaxies, we can go and study different things. We can study the stellar kinematics. We can study the gas kinematics in this vicinity. Okay? For example, if there's a disk around the black hole, you might find a certain component which is redshifted, certain component which is blue shifted. And then we can also look at, for example, many galaxies have laser emission at radio frequency detected from the nuclear region. We can image those laser spots and find out at what velocities they're moving, how far they're from the central object, and then you can go and infer the motion and the presence of a black hole and estimate its mass. Then the other ways are, for example, at X-ray wavelengths. From the disk itself, you can get an emission line of iron called K alpha line, the L to M transition, and the lines get affected by the Doppler shift, the gravitational redshift of a massive object, and the line profiles can infer the existence of a black hole. So you can do many different ways of trying to determine the mass and the presence of a black hole. And from that, we find that all galaxies with a bulge have a massive black hole. You can estimate the mass of the black hole.
But that's based on the galaxies we have observed, and if they have a supermassive black hole.
It's based on the galaxy that we have been
it's based on statistics. How can we make a blanket statement?
If you observe, 400, 500 galaxies and each one of find that, it's a fair assumption to make that it's probably universe. If it is 10 out of 10, you would say, okay, maybe I should have a larger sample. But this has been done now for hundreds of objects.
Okay.
So the fact that we have been able to identify black holes in several hundred objects confirms that it's probably universal. But the question is, for example, if I take very small galaxies, what are the kind of black holes do we have? We have supermassive black holes at all. So there also we've been able to make some takes. They don't seem to be supermassive like more than a million solar masses, but they seem to have intermediate mass black holes, 10 to the power of 4, 10 to the power of 5 solar masses. So that's a kind of frontier where the field is right now. Yeah. Any other question?
Sir, is it possible that the radial loudness depends on the matter that is accreting in the accreting disk and not on the property of the black hole?
Possible. It's probably a combination. So this is what this slide tells you. We'll finish in 15 minutes. Okay, 15 minutes. So this is one of the early attempts to find out about what is radio loudness. They defined a parameter called the radio loudness, which means basically the ratio of the 5 gigahertz flux versus the optical flux. And if this ratio is greater than 10, which means log R greater than 1, they call it radio loudness. So on the y-axis is plotted the radio loudness. So anything greater than R greater than 1 is radio loud, that means shooting up a powerful radio jet. On the x-axis, what you have is the mass of the black hole. Okay. Now what you see over there is that when you go to mass of the black hole greater than 10 to the power of 9 solar masses, they're all radio loud. Right? Less than 10 to the power of 8 solar masses, they seem to be all radio quiet or radio weak. In that middle range, they seem to be both categories. I mean, that at least tells you that the mass of the black hole is probably playing some role. But it also tells you that is not the entire story, because in this range, you have both radio loud and radio quiet objects. So definitely the mass of the black hole has a role, but it's not the whole story. So then what could be the whole story? Then the other natural thing to talk about is, because you remember we talked about the curved black hole, the higher efficiency. There's a spin on the black hole output. So maybe when people said maybe the spin is the important factor. But then when people measured the spin, they found of black holes. I'm not getting into details of measuring spin because that's a long story. Okay, they found this is, they defined a spin parameter. This is the angular momentum. This is the velocity of light. This is the gravitational constant. The mass of light. So this maximally rotating A will be about 1. But you find that even a million solar mass black hole, which is similar to that of our galaxy, can have spin of about 1. So spin alone is also not this answer, because we know of black holes which are spinning maximally, maximum possible spin, but they're still radio weak. They're not shooting out powerful jets. And several of these examples, I've just listed 2 examples over here, 2 separate galaxies over here, and so that is not good tested. So is mass and black hole is a high mass and a high spin both required to produce these jets? Is it a combination? We don't know. We actually don't know the answer. I think one needs to actually measure accurately for the spins of objects which have high black hole mass and are radio quiet. And I'm not aware if that has been done as yet. So that's an exercise which one has to do. But coupled with all that, what you said, the variable of accreting matter would be important. The variable of accreting matter. And the other fundamental thing which would be important is actually what role do magnetic fields play, if at all. Magnetic stress is building up, having to actually accelerate plasma to high velocities and throw it out, but we don't really know. So these are aspects which are likely to play a role. So the radio loudness, the radio quietness dichotomy is still unsolved, but we are making some little bits of headway with the new observations and data that we have at hand. With a slightly better understanding, hopefully, when many more of these nearby AGA are imaged with the kind of resolutions that we are able to achieve today for just a few objects. Now, related to this question of jets being launched in luminous objects and 10% being radio weak or radio quiet, or 90% of the majority being radio weak or radio quiet, the question which is also being asked is, do these objects all go through phases? In the sense that, they spend 10% of the time in the radio loud phase, that's where we catch them, but then they become radio weak, and then we don't see them as radio loud. So is radioactivity episodic? Is it recurrent? Now, if you want to ask that question, then you need to get into this field of recurrent or episodic. What is the evidence for it? Or is there any evidence at all for it? So first, let me show you an example of a source what it might look like if it is a dead source. Suppose jets have gone and the jets have switched off, and you have this diffuse load solution. They're going to radiate energy as long as possible, depending on the energy of the electrons in the field. You can see this probably had hotspots at one period of time, but you can see there's a dip in the middle, so the electrons are diffused outwards. And because the higher energy electrons radiate energy faster, the straight sort of spectrum has also begun to curve, and so keep curving to lower and lower frequencies. And after about a few hundred million years, it's going to just be very difficult to detect. Now, if this source were to start off again, then it might look like a galaxy like this, where there is a new pair of jets which are squirting out from the galaxy. So there have been attempts to study these kinds of objects to see how prevalent they are. And so far, I think there are about 150 or so are known. So given the numbers, I'm not so sure that it is the right explanation in terms of the episodic activity being responsible for the darkness or the brightness. The fact that some of these galaxies can completely disappear is something which one studies, and both from radio as well as X-ray wavelengths. Here you can see the hotspots are diffusing outwards. They're weaker, and a new pair of globes are coming out. And the new ones, the new jets, have a straight spectrum because the radiative losses have not become significant. The outer ones, it begins to curve because the high energy electrons are radiating away energy much faster. So these are more examples where new jets are being formed right in the nucleus over here. More examples. Okay, I'll stop with that. More examples. Small sources. This is the one I wanted to mention. You see here, there's a diffuse blob of plasma. Okay? Diffuse blob of plasma. And this is actually, what is seen on the left is just X-ray emission. The left one is an X-ray map. Okay. Now, it looked like a double source. So what we wondered was that whether it was a very old source, where there are old relativistic electrons, very old relativistic electrons, but they are probably, so you don't see significant radiation from them. But whether the cosmic microwave background photons could have scattered off the electrons to give you X-ray emission and giving you an X-ray double dome source, where is the radio in the middle. So we actually made deep observations with the GMRT to look for it. We do not see it. And so we are sticking to the story that this is a very old radio galaxy where the radio emission is no longer visible, but because of inverse Compton scattering, we are seeing it in the X-ray region of the spectrum. One way to test it would be to see if there is X-ray polarization. X-ray polarized emission is something which is just coming into the field right now. Earlier, all the X-ray images were complete density images, but X-ray polarity in the upgoing field. And that will actually give us clues whether that is correct or incorrect. And there are some more examples. But the total number that we see are very small. There are also examples of this specific activity. I talked to you about these jets in holes. In some clusters, you see multiple pairs of holes. So you know that bubbles of plasma are coming out. But the total numbers are still very small. But one thing which seems, at least from a preliminary study, to show that this recurrence of activity seems to be closely related to the supply of gas. And how do we look for the gas? We try to look for cold gas by looking at either atomic hydrogen or molecular gas. Molecular gas has been successfully very, very difficult to detect. But almost every object where we detect absorption of radio continuum by hydrogen gas front, we actually, the numbers are slightly to do some examples. There are observations with the GMRT. This is one observation with the RCAA telescope, which sadly proved that it exists. But the numbers are very few. So we need more numbers to really see this recurrent of activities due to object activities due to supply of gas. But clearly there has to be some supply of gas for jets to squirt out. So the bottom line is probably the mass of the black hole, the spin of the black hole, and the supply of gas. The which all play a role in trying to produce jets. And in terms of the collimation of these features, magnetic fields must be playing a role. At least in some scales, we can image the signatures of the magnetic fields by the way the inferred field orientations from polarization measurements. But how important a role it plays right in discovery balance, discovery associated with black hole is something which we will only learn as time goes on. We are in an period where major advances have been made with the new telescopes that have come into operation in the last decade or so. A lot of progress has been made. But the next major step will probably be with the square kilometer array, which Yash will talk to you about at 4 o'clock. Right? So I think I'll stop here. I'm not trying to pick up this and we can spend about 5 or 10 minutes discussing doubts. I know I went through a bit rapid. I just wanted to give you a flavor of the different aspects in which the field is developed. I did not touch much on magnetic fields because that's a bit more complicated, except to illustrate to you that the depolarization of the emission can establish the tensor approaching us. So we can spend 5 minutes to take questions.
So to look for the accretion in accretion disk and the jet activities for the dichotomy, can we relate the mass of the host galaxy or the stellar activity over the galaxy and find if it is like
yeah. Actually, I'll show you the Gregorian relationship where the mass of the black hole is related to the velocity dispersion of the bulge. And velocity dispersion of the bulge effectively means the mass of the bulge. Okay. For massive it is, the higher the velocity dispersion. But it seems to have no relationship with the mass. So the way the bulges have developed seems to be intimately related to the black holes, but not necessarily with the whole galaxy. So we plot the velocity dispersion of the whole galaxy, spiral galaxy, for example. In elliptical galaxy, the bulge is of the galaxy, but it is very little to do with the velocity galaxy. Also the bulge that seems to do.
stellar activity of the galaxy has coordinating.
That's a very interesting question, actually. See, stellar activity in the nuclear region. Now, if there is inflow of gas to the nuclear region, which is supplying fuel to generate these jets, some of it will also get into star formation. So you should see evidence of this star formation in the nuclear region as well. In some cases you do, in some cases it's less obvious. So there's a major project going on right now trying to look at nuclear star clusters and AGN. Okay. One is actually trying to distinguish them from optical and radio X-ray information and to classify these nuclear star clusters, which is a nuclear star cluster, which is AGN. What kinds of galaxies have nuclear star clusters, what kind of AGN have, what kind of galaxies have only AGN, what kinds have both. And so it is still in the early stages of trying to parameterize and understand the relationship too. But the overall galaxy probably will not have an effect, but the star formation in the nuclear or the circumnuclear region should be related in some way, even if it is not always obvious. Yeah. It's an interesting question, but it is something which people are still working on. Any questions from this side?
Any online question? In case if you have any question, please raise your hand.
Sorry, is the question from the chat, Prakash?
Yeah, there are no questions in the chat sites.
Okay.
I just asked if they have any questions so they can raise a.
Okay, Jamil, you're looking after today. Okay.
Yeah.
Okay.
So what can the depolarization of light tell us about the gas present?
what does the depolarization of light tell us? Okay. Now, suppose I had a source of emission, all right, and let me just say that it has vectors in a particular direction. Just for argument's sake, you actually cannot make out the difference between 180 degrees and 350, but ignore that for a time. Now, what is the way depolarization arises? Suppose this object was 20% polarized. Let me just say 20% polarized, which means that the polarized intensity divided by the total. Intensity of flux. You say intensity actually subsets. Alright. Now, let me say this to you. Now, if I were to, if there was nothing in between, right? The emission will just come through, right? And you will see 20% polarization. Now, let me say that this source is bird a bit because it's for particles. Now, I have a medium. I have a medium over here, and the medium is never uniform. So let me just take, suppose it's a uniform. It has one electron density and one parallel component. They know irregularities all. Okay. And see, let's see the parallel component. It is completely uniform, and it is a constant electron density. Okay. Then what happens is that the position angle chi lambda would be the intrinsic position angle plus Rn. I'll come to Rn here. That is fine. Rn is sort of, except for some constants, would be integrated along the line of sight. So now I'm taking a condition where everything is uniform. Right? What will happen in that case is that Ne is constant, here parallel is constant, this becomes constant. So if I observe it along a wavelength, say, document say, then I will see the same source, but all the vectors will be rotated by the same amount. Right? But the next degree of polarization which I will get if I had a telescope beam of this size will be the same because everything is rotated by the same. Now, let me say this. I have all kinds of objects. Some are large, some are small. So there will be on each blob has its own electron density and field elevation. Then what will happen is that depending upon the line of sight, what cuts it, each one will be rotated by a right? So when I observe with a telescope beam and all these vectors are inside it, they will all add up to give me a net value of polarized intensity which will be good. So all I'm measuring is the degree of I mean, I can make this at a number of wavelengths, all right? Then I can, this degree of polarization. What I can also do, for example, I can actually measure the position angle at a large number of wavelengths and get a value for the slope of this line. Right? If I have a slope of this line, then I have a measure or an average measure of the parallel. I cannot distinguish between the two. But if I have a rough estimate of what electron density is, then I can get a component of magnetic field. Or if I have a component of magnetic field, I can get a component of, I can estimate electron density. So I can do this not only for extragalactic objects, but I can also do it for objects like pulsars, where I have an independent measure of electron density, so that gives me a measure of the vector. The way actually this depolarizes because of this, I can reconstruct it backwards. Actually, one thing is to understand the properties of it. I'm not getting into too much detail of how we do it, but we can infer some of the properties. But I have only illustrated to you what happens if there is a screen in front of it. Right? Now, if there is a screen in front of it, all I'm saying is that the beam is so large, so I'm averaging it out. Right? But I can increase the resolution. Right? If I increase the resolution so that I'm measuring each one of them separately, then I can measure the rotation measure from each point over there, but my degree of polarization will come down. By using this measure, I can find out the scale size of irregularities over there. Okay, what kinds of irregularities exist over there, and I can also see that if I have enough resolution, I can get a high value of rotation measure without it depolarizing, because I'm able to resolve complex structures. But what I talked to you over there is a screen. It need not be a screen, because the source which is emitting may also have thermal particles over there, because these are the thermal particles which are rotating. So then what happens is, if you think of a ball over here, that radiation is coming from the back as well as from the front. So the one which is coming from back will be affected by it. So their resolution is not going to help. So you can try to distinguish between whether it hit the source or it's in the screen by making. So there are a lot of different things you can do with it, but you need to make observations and different resolutions of polarization and try to get the degree of polarization and the position angle of the radiation at different points. Yeah. So does that answer your question? I mean, not completely, but you're not getting into too much of detail in your problem. So maybe we'll take one last question if there is any. We'll wait for tea. Everybody wants tea. So we'll wait for tea. So we'll meet here at 4 o'clock. And Yashwant is going to talk to us about thanks.
Thank you. Thank you.
Okay, I'll share these. I'll send it to Ravi. He has your email. So I'll send you the PDF files. Anyway, I mean, here I may not come to the class, but you'll not sit here.
Recording stopped.
How do we know that they're polarized? Because you can measure the polarization with telescopes. I mean, the thing is that this is a bit about polarization. You know the Stokes parameters. Okay. So the thing that what happens is that I mean, if you look at it, if there is a net degree of polarization, the electric vector has a preferred angle, right? So there would be two parameters in characterization. One is the